Hello, I'm Ved. My teammate Parimuksha and I attended the course titled Neural Network Implementation and Deployment. Over the past few months, we studied several topics and we are excited to share everything we learned with you. The topics we will be covering in the video are neural networks and how they work, an introduction to parallel programming, using APIs for app development, and lastly, a summary of the research papers we read.
So, let's start with neural networks. What is a neural network? A neural network is nothing but a computational model inspired by the way the human brain works. It consists of layers of simple computing units called neurons. By combining many such neurons in multiple layers, neural network can learn complex patterns from data. Before diving deeper, let's quickly define two essential terms. Forward propagation it is the process of passing input data through a neural network layer by layer to produce an output. During this stage, calculations are performed to determine the output values using the current weights and biases. Second, backward propagation. Backward propagation is the training algorithm used to improve the model. After the forward pass, the output is compared to the actual target and the weights are updated so that the network makes better predictions. Now, let's talk about forward propagation. To better understand each step, let's take a simple neural network with one input layer, one hidden layer, and one output layer. First, each input value is multiplied by a weight connecting the input to the neuron in the next layer. All of these terms and the bias are then added together. Here, we're adding I1 multiplied by W1, I2 multiplied by W2, I3 multiplied by W3, and the bias B1. Next, we pass this value through an activation function, in this case sigmoid, to obtain the final output of H1. The output from this layer becomes the input for the next. Same calculations are performed for each layer. This process repeats for each layer. The last layer of the network produces the prediction of the network.
Now that we have the framework of the model working, we needed to adapt and learn so that it better fits the training data. To do this, we used backpropagation. This comprises of four steps. First, we calculate the output error. To do this, we take the derivative of the activation function of the output value. Since we use the sigmoid function here, the derivative is equal to x into 1 minus x. We then multiply that with the deviation of the output value from what the correct answer should have been. Next, we find the error of the hidden layer. The error of a hidden node is equal to the sum of the error of the output nodes into their corresponding weights into the activation derivative of the hidden value. Now that we found the errors, we use it to update the weights. The change in the weight between two layers is equal to the error of the lower node into the in value of the upper node into the learning rate. The learning rate is a constant that's used to control how quickly the model changes. Too high a learning rate will cause it to change too much to ever actually reach the correct value because it will just oscillate around it, while too low a learning rate will cause it to take an extremely long time to actually run. We then built our own neural network consisting of 3 input nodes, 11 hidden nodes, and 2 output nodes. We then replaced all the calculations with a matrix format to make the code quicker to run and easier to read. To properly understand the mechanics behind this, we did all of this without using any library to replace parts of the process, other than using NumPy for easier matrix multiplication. Now that we understood how neural networks work, let's take a look at one of the techniques that makes them so efficient: parallel programming. Parallel programming is when we have multiple calculations occurring at the same time rather than one after the other. This greatly increases efficiency by minimizing the amount of computing power that we leave sitting idle. Most of it ends up being used, improving how quickly the program can run. To better visualize this, let's imagine a factory making cars. Let's suppose that every worker just adds one part to the car and then passes it to the next worker in the line. But they don't start working on the next car until the first one is done. Then, most of the time is just spent waiting for someone else to finish their section of the job. Whereas, if each worker worked on their own car, several cars could be built in that same time and no one would be left sitting idle doing nothing. So, how does this work? Generally, we use libraries such as CUDA to easily allocate work to the graphic processing unit, which is a part of a computer that's optimized for parallel programming. We distribute the workload among several threads, with groups of threads forming blocks. For example, here we have 4 blocks, each of them with 4 threads, so we can totally have 16 calculations occurring at the same time.
Next, we also explored applications of existing AI models via APIs. I learned about RAG agents and LLMs and built an app using the concepts. Before we look at the app, let's have a short review of RAG agents and LLMs. LLMs, or large language models, are advanced AI models trained on vast amounts of textual data. They are used in understanding and responding to human language. RAG agents, short for Retrieval Augmented Generation agents, are systems for optimizing LLM's output so that it references knowledge base outside of its training data before generating a response, enabling context-aware conversations. Large industry-grade applications need to manage large amounts of data and API calls. They use microservices for that. What are microservices? Well, they are small independent services that perform a specific function within a larger application. These modular building blocks can be developed, deployed, and scaled separately, allowing for greater flexibility and efficient management of complex AI systems. Generally, one service receives user input and pass it on to the app's backend, which invokes an API call to the LLM client service, where the response is generated by the LLM, which is then received by the user. Let's talk about my project Gitwit. Gitwit is a smart AI assistant which can interact with GitHub repositories. It can answer queries regarding issues, pull requests, etc. using RAG, LLMs, and GitHub API. Well, how did I make it? First, I set up API calls to the desired LLM model using the LangChain framework in Python. Next, we fetched the required external data from a repository using GitHub API, which we stored in a vector database. Then, all we need to do is get the prompt or the query about the repository from the user and wait for the LLM's response. You can see a small snippet of my code for this app on the right. Here is a short demo of Gitwit in action. You can see that we have asked a question regarding the issues in the repository related to flashing messages. The LLM is invoked with an appropriate query and soon we receive a response.
Meanwhile, I learned to make an app that added custom backgrounds for objects. This could be used in advertising or animating shows. First, I used NVIDIA's KTAP template to quickly build a custom UI for it. Then I added code to interface it with the API. First, I put a URL which actually links it to the correct site, and then you have to give a API key which gives you permission to actually use that API. After that, we just need to replace the variables required with the input from the UI and save the response we get. Lastly, we import the object that we want to model and replace the background file with the location of the image that we already generated.
These apps are great, but GPUs are really expensive. We need more and more efficient models to run them sustainably. One attempt of achieving this was made on 18th February 2025 when the paper DeepSeek V3 technical report was published by a Chinese company. Let's first see what is DeepSeek. DeepSeek is an open source LLM trained by a Chinese firm. It has 671 billion parameters in its version 3. It is quite cost efficient too, trained in about $5.6 million, where competitors like GPT-4o are trained in hundreds of millions, sometimes even billions of dollars. It directly competes with closed source leaders like GPT-4o and Claude 3.5 Sonnet in terms of performance. DeepSeek pushes boundaries for open source AI, showing how smart engineering can make massive models fast, cost effective, and competitive with industry leaders. This paper mainly focuses on improving or addressing the following issues with the last version. Number 1. High computational and memory costs. Number 2. Load balancing in mixture of experts or more. Number 3. Training speed and precision. Number 4. Improving model abilities in reasoning and multi-domain strengths. Addressing these, the first thing they looked at was smarter attention mechanisms. They used multi-head latent attention, which employs compressed representations to drastically reduce memory use and speed up model calculations. Previous models used more memory intensive attention that limited scale and efficiency. Second, implementing balance expert usage via auxiliary loss-free load balancing, which introduces a novel way to ensure all expert components of the model work evenly and efficiently, solving performance drops that older methods face due to imbalance. Third, accelerating learning by use of multi-token prediction, which is basically training the model to anticipate several future words at once rather than just one, leading to richer learning and better predictions, unlike the more limited single-step training before. Fourth, efficient training process using FP8 mixed precision, which adopts 8-bit calculations for most training steps, allowing for much faster and cheaper model development. Prior approaches relied on larger numbers, resulting in higher cost and slower processes. In a nutshell, DeepSeek V3 sets a new standard for open source language models. It's efficient, scalable, and remarkably strong across language, coding, and reasoning tasks. The project exemplifies how thoughtful architecture and system design can unlock powerful AI tools for broader use.
In summary, we learned how neural networks work and how to program them. Then we learned techniques to make them more efficient. Then we used that to build and customize our own AI models. Lastly, we learned to read and analyze several research papers pertaining to that field. This has been an incredible and insightful journey. On behalf of my team, I'd like to thank our mentor Pune Safoyaniku and the entire SIP staff for making this possible. Thank
Thank
you.
you.